Thanks for the introduction. And besides the T1 and T2 mapping, the Cine imaging reconstruction was also investigated. Okay, sure, thanks. So as we know, quantitative T1 mapping, including the native T1 mapping and the T2 mapping, are important myocardial tissue characterization methods detecting a number of cardiovascular disease. And Cine imaging is widely used for cardiac function assessment. And for T1, T2 mapping, the multi-contrast images is rarely required for pixel-wise fitting. And for T1 mapping, the inversion pulse or saturation pulse is usually used to introduce T1 contrast. And for T2 mapping, the T2 probe with different algorithms are usually used to introduce T2 contrast. However, for cardiac mapping, to reduce the cardiac motion and the respiratory motion, the acquisition requires ECG triggering and should be under-braced, so which has the limited imaging coverage and low spatial resolution. Also, the 2D acquisition will have the low SMRA and through-plane motion issues. And the T1, T2 mapping is usually performed in separate scans, which will cause the misregistration of the T1 and T2 maps. So the 3D free breathing mapping techniques have recently been investigated. For example, the diaphragmatic navigator has been used to enable 3D free breathing T1 mapping. However, the respiratory gating has low acquisition efficiency and may result in the long scan times. And the through-plane spatial resolution is very low. And recently, we have proposed the free-running T1 mapping technique, which is the acquisition is IR prepared following by the 3D gold-angle radio sampling. With this technique, the whole heart isotropic T1 maps can be generated for multiple cardiac phases. And we aim to extend this technique for both T1 and T2 mapping. And the continuous acquired data can be used for Cine reconstruction. And here shows the sequence diagram on the left side. Besides IR preparation, we also introduced the T2 preparation with 2 different algorithms to introduce different T1 and T2 contrasts. And these 3 different preparation patterns are alternatively performed during the whole acquisition. And following the preparation, the 3D gold-angle radio sampling is performed and free breathing. And the ECG signal is recorded for retrospective cardiac beating. And there are 3 steps to introduce the influence of respiratory motion and cardiac motion. Firstly, the 1D self-navigated respiratory motion signal is extracted from the case-based center. And to enable the data for being the 2 different respiratory motion states, and the inter-beam translational motion was corrected. After this step, to reduce the cardiac motion, the cardiac beating was performed for a given cardiac phase. Okay, here shows how we extract the 1D respiratory motion signal. In the 3D radio acquisition, each spoke will sample the case center, which should contain the contrast change and the respiratory motion and the cardiac motion. So here shows the 5 independent components. And after Fourier transform, we can get the spectral power density function. Given the IR representing time and the T2 IR representing time, we can see the IC3 should reflect the contrast change, and IC5 with the highest spectral power in the respiratory frequency range contains the respiratory motion, which is band pass filtered to get the self-navigated respiratory motion signal. Here shows is a comparison with the respiratory bellow signal. With this motion signal, the respiratory the case-based data can be binned to different respiratory motion states, and inter-beam 3D translational motion was corrected. And after this step, for T1 and T2 mapping, the spokes were selected for given cardiac phases, which should have different T1 and T2 contrasts. To exploit the contrast redundancy, dictionary-based low-rank compression was performed along the contrast dimension to get 5 singular images to be reconstructed. And HD Pros was used to reduce the undersampling artifacts. And HD Pros is a multi-contrast 3D patch-based low-rank reconstruction method. It selects similar 3D image patches for all the contrasts. And after tensor stacking and high-order single-value thresholding, we can get the denoised images. After the HD plus reconstruction, digational matching was performed to get the T1 and T2 maps. And for Cine reconstruction, the cardiac binning was performed for a series of cardiac phases. And after the digational-based low-run compression, the first singular images with the highest SMRA was reconstructed for each cardiac phase to generate the Cine images. This sequence was implemented on the 1.5 Tesla Philips scanner, and standard T1, T2 phantoms were acquired with the free-running sequence in compared with the 2D AR spin echo and the 2D multi-echo spin echo method. For in vivo imaging, 10 healthy volunteers were recruited, and the speed resolution of the free-running sequence is 2 millimeters at tropic, and the total acquisition was about 11 minutes. For in vivo T1 and T2 reference, the 2D Molly and the 2D gradient spin echo method was performed. And for Cine reference, the traditional stack of short-axis Cine images were acquired on 7 subjects. Here shows the phantom T1, T2 mapping results. It can be seen in the Molly method and estimate larger T1 values, and the 3D radio method achieved better accuracy. And for T2 mapping, the 3D radio method tended to estimate larger T2 values, but in the myocardium T2 range from 40 to 50 milliseconds, the 3D radio method achieved better accuracy than the Grace method. Here shows the 3D diastolic T1, T2 maps for one healthy subject from base to apex and the long axis short and the long axis view. To evaluate the distribution of T1, T2 values measured with the 3D method, the AHA segment analysis was performed. The value of each segment was the average of all healthy subjects and shown in the both side plots. And the value in each segment can be visualized in the box plots. It can be seen that in the inferior segments, the T1 values tend to be lower, which may be caused by the residual respiratory motion. And the septal segment in the apex, which will have the higher T2 values, which may be caused by the partial volume effects from blood. Here shows the 3D T1 maps comparison with the 2D Molly and the 2D Grace methods in 2 healthy subjects. And 3 short axis slices were included for the 3D T1 maps. And the mean and standard deviation of the T2 and the T1 values in the septum was measured from the 3D and the 2D methods and are compared here. It can be seen that similar to the phantom results, the 3D method has higher T1 values than Molly and slightly lower T2 values than Grace. And the standard deviation of T1 T2 was lower. Was lower than the 2D method. And here shows the Cine comparisons with the 2D and with the. Should I go on? Sorry.
Please accelerate so that you're rethinking things.
Okay. Here shows the comparison of the 3D Cine images with the 2D Cine images. It can be seen the blood myocardium contrast is not as good as the 2D Cine images. And to evaluate whether the 3D Cine images can be used for cardiac function measurement, we measured the end-diastolic volume, end-seat volume, and the injection fraction from the 3D and the 2D methods. It can be seen it is plausible to use the 3D Cine images for cardiac function measurement. So in conclusion, we have proposed this free-running technique to generate co-registered T1, T2 maps and isotropic whole heart Cine images in a single acquisition. And this sequence can be used for post-contrast imaging also, and the scan time can be reduced to within 5 minutes. And due to the residual respiratory and cardiac motion, it will cause the image blurring. So this technique needs further validation in patients to detect its ability of testing cardiovascular disease. And thanks for your attention.